Hey everyone, and welcome. Today we are diving deep into the world of electronics to decode one of the most essential, most common components out there, the resistor. Seriously, these things are in everything, and we're going to figure out exactly what they do.
You know what I'm talking about, right? If you've ever cracked open an old remote or looked inside your computer, you've seen them. Hundreds of these tiny little components that look kind of like colorful bugs just sitting there. So what's their deal? Let's get into it.
Visit youtube.com/avidsystem and don't forget to subscribe.
And here it is, the big secret. A resistor's main job is to resist, or, limit, the flow of electrical current. The best way to think about it is like a faucet on a pipe. You turn it to control how much water gets through. Resistors do the exact same thing, but for electricity. They're basically the bouncers at the door of your circuit.
So how do we actually measure this resistance? Well, we use a unit called the ohm, and it's represented by that cool Greek letter omega. It's super simple. The more ohms a resistor has, the more it pushes back against the current.
All right, so how do we know a resistor's specific value? I mean, it's not written on there in plain English. Turns out they have their own secret language. And this language kinda has two different dialects. For all those tiny, super common resistors, their value is actually encoded in a series of colored bands. But for the bigger, more heavy-duty ones, the value is written out in a standard code using letters and numbers. Just two different systems for two different kinds of jobs.
But here's something that's absolutely crucial to understand. Nothing is perfect, especially in manufacturing, and that's where this idea of tolerance comes in. It's just a percentage that tells you how close to its stated value the resistor actually is. So a 100 ohm resistor with a 10% tolerance, it could be anything from 90 to 110 ohms in reality. So yeah, the lower that percentage, the more precise the component is. And this precision is all standardized into what we call E-series. You can see here as that E number gets higher, the tolerance gets way tighter. An E6 resistor, for example, has a pretty wide 20% tolerance, which is totally fine for simple circuits. But something like a high-precision E96 resistor, that's accurate to within 1%, which is absolutely critical for really sensitive electronics, like scientific measuring equipment.
So now we know how to identify a single resistor. But here's the thing. In any real circuit, they almost never work alone. They're team players. So let's look at the two main ways they get connected together.
First up, we've got the series connection. And this is exactly what it sounds like. They're just chained together, one after another, creating a single one-lane road for the current to travel down.
Now, series circuits follow some really straightforward rules. Most important ones are, the current, the flow, is exactly the same through every single resistor in that chain. But the voltage? That gets divided up among them. This is actually super useful. You can use it to create what's called a voltage divider, which is a really common way to get a specific lower voltage from a higher one. And the total resistance? Easiest part of all. You just add them all up.
So here's the key takeaway, the one thing to remember. When you add resistors in series, you always increase the total resistance. Every single one you add just makes it that much harder for the current to push through.
Okay, so that's our first setup, resistors in series. But what happens when we give the current options, when we give it more than one path to follow?
Well, that brings us to the other way of connecting them, in parallel. Now, instead of that single file line, I want you to imagine opening up new lanes on a highway. The current now has multiple paths or branches that it can take all at the same time.
And the rules for parallel circuits? They're pretty much the exact opposite of series. Here, the voltage is the same across every single branch, but now the current is the thing that splits up, flowing through all the different paths. This is great when you need to give the same voltage to a bunch of different components, but it also leads to the most surprising rule of all.
Yep, you heard that right. It feels a little weird, but when you add more resistors in parallel, you are actually decreasing the total resistance. It makes sense if you think about it. By adding more lanes to the highway, you're making it easier for all the traffic, or in this case, current, to flow. The total resistance will always end up being smaller than your smallest individual resistor. Kinda cool, right?
So let's just put them head to head for a second. Series, one path, a daisy chain. The current is the same for all. The voltage splits up, and the total resistance just goes up and up. Parallel, multiple branches, the current splits, the voltage stays the same, and the total resistance actually goes down. Getting this difference is like 90% of the battle in understanding basic circuit design.
Okay, so we've covered how resistors hook up in series and parallel, but there's one more really practical detail we need to talk about, and it has everything to do with their physical size.
I mean, you've definitely seen this, right? Some resistors are these teeny tiny little things, and others are big and chunky. It has nothing to do with their own value, so what gives?
The answer is all about power. See, as current flows through a resistor, it does work, and that work generates heat. A resistor's physical size is basically a billboard for how much heat it can get rid of safely without burning itself up. We call this its power rating, and we measure it in watts.
Now this little guy, the quarter-watt resistor, is probably the most common size you're ever going to see, especially in hobby electronics and other low-power stuff. It's a fantastic all-rounder, but you definitely can't use it for everything.
And this right here is why it matters so much. If you try to push way too much current through a resistor, it just can't get rid of the heat fast enough. It gets hotter, and then poof. You get that little puff of magic smoke, a really bad smell, and a circuit that doesn't work anymore. Choosing the right power rating isn't just a good idea, it is absolutely critical.
So let's just do a quick recap. We've gone from looking at these mysterious little striped things to understanding their secret color code, figuring out how they work as a team in series and parallel, and now understanding the super important real-world limit of their power rating. You basically have all the fundamental rules of resistance right at your fingertips. See, resistors aren't just these boring little parts. They're powerful tools for controlling the flow of electricity. You can use them to dim an LED, to create a specific voltage, to protect a more sensitive component. They're literally in every circuit that runs our modern world. So the real question is, now that you know how they work, what are you going to build? Thanks for tuning in.
Thanks for watching.